So eventually that will resolve itself. But again, you can use remote clocks from the NTP.org website, navigating to the time servers link and just finding time servers that are in your vicinity, such as from a university or a big company that's been gracious enough to publish NTP servers. And the suggestion is that you supply your NTP server with at least 3 clocks so that it can determine which clock is the most accurate, and also for redundancy. So note, ideally, you should supply, which explains why we saw 3 entries for Red Hat Enterprise Linux clocks in the default configuration. So you should supply your etc.ntp.conf file with at least 3 clocks for the following non-inclusive list of reasons: to determine accuracy, which is built into the network time protocol, as well as redundancy. In the event that one clock goes offline, at some point the network time protocol daemon will determine that it's offline and attempt to contact another clock. And the NTP daemon is always checking to see whether or not a clock's available and if it's still accurate by maintaining a list of offset, delay, and jitter direct values, metrics, and calculates based on those metrics. So with that said, we should place other clocks in. Now, in the case of the Red Hat Enterprise Linux clocks, let's nano etc.ntp.conf. They'll definitely respond. These pool clocks, if we uncomment them in addition to the 199 hosts, and we could even add, we have a clock internally at 100, the Media 1 box, and then restart the NTPD daemon using service NTPD restart or etc initd. Here's an optional way, etc initd NTPD restart. Now when we re-execute NTPQ NP, you'll see all of the clocks. Notice the internal clocks haven't resolved as we expected. However, the external clocks have. And we see that of the 3 Red Hat Enterprise Linux clocks with the pool addresses, 2 of them are at stratum 2, whereas the third's at stratum 3. The 2 that are at stratum 2 reference stratum 1 clock. So this 216 and this 217 clock reference these distinct IPs, 132 and 18 respectively, at stratum 1. These clocks in turn reference official time sources. So we could, if we wanted to, directly reference the stratum 1 level clock by updating our configuration. Let's nano it, and we'll just place it somewhere on the list. Doesn't have to be in any specific order. NTP will make the determination as to the accuracy by simply contacting the clock. Let's restart NTPD, clear screen, and then rerun NTPQ, the query utility, to determine what's going on. Now currently we see that the 132 clock was contacted. It took a while. Also notice it took a little while, but the 100 clock was contacted at stratum 3. So it takes a while for resolution to happen. By a while we mean sometimes 10 seconds up to a minute or a couple minutes, depending on network latency. So we do have a stratum 1 resource. And in all likelihood, the stratum 1 clock will become our default clock because it's more accurate than any of the other clocks. Also notice that with the stratum 1 clock, it references a GPS source for time, which is accurate. So this clock, in all likelihood, will become our default clock. But again, for each clock, metrics such as when it was contacted, the pulse interval, if it was reachable, the stratum that it's at, whether or not it's up, the delay, offset, and jitter are maintained for each and every clock that we communicate with, and NTP crunches the numbers to determine who's accurate. It still has not determined which clock will become its master or trusted clock, but it will at some point. So indicate as many clocks as you'd like. Ideally, specify at least 3 clocks, and depending on the clock that becomes our default clock will determine the stratum level at which our local system operates. So if the stratum 1 clock becomes our default clock, we become a stratum 2 clock for which internal resources can be used to synchronize against. For example, a Cisco router could use or could synchronize against our internal clock. That would certainly not be a problem. In fact, let's SSH into the router. And once there, we'll just navigate into the config mode and execute the NTP server command, followed by the IP address of our local system, which is .10, the Red Hat system, Enterprise 5. This will attempt to synchronize the router, and now when we execute show NTP associations, we'll see at some point that it has contacted and assigned a stratum level to our clock. Notice the router is using currently the Media 1 box, 75.100 at stratum 3. But over time, when it is able to communicate with our internal system, the new system that's updated the configuration, it will determine that it's a stratum 2 level clock and use it over the stratum 3 level clock, Media 1. So it'll take a little while, but it'll update, and throughout our studies of other items, we'll check in just to see where it's located. But again, just to recap briefly the way NTP works. First and foremost, it works without much intervention. There isn't much for you to do other than to define servers that are to be consulted, NTP servers, in the etc ntp.conf file. You also need to, of course, start the service and ensure that NTPD starts in the desired run levels. But the key thing is to assign a server or more in etc ntp.conf, and you may optionally apply security to the configuration file, but then you need to ensure that the other NTP peers and servers with whom you communicate are configured with the appropriate security directives to be able to communicate. So if you turn on security on one after consulting the documentation, be sure to turn on or enable security on the others, since NTP servers will naturally function as pairs if they're referenced via the etc ntp.conf file. The protocol works in a hierarchical nature, with stratum 1 clocks being the most accurate clocks because they're connected to external time sources such as GPS. And it goes all the way to stratum 16, which is considered inaccurate and should not be used. So whenever you start NTP, initially all clocks are set to stratum 16 with the exception of the localhost clock, which is assigned stratum 10. Stratum 16 means the clock is not to be trusted. However, 15 through 1 should be trusted. And the differences between the strata levels are minor and are measured in milliseconds and not in full seconds. So even if you synchronize at a stratum with a stratum 12 clock, you're likely to be just slightly off from synchronizing with a stratum 2 or 1 clock. So go ahead and find a clock to synchronize with at ntp.org. The site's coming back pretty slowly, but we'll look at it later on to see where you can pick out lists of clocks. A standard hierarchy in a corporate environment is to set up one or more, preferably 3 internal trusted time resources. So you pick, let's say, 2 Linux boxes and maybe a Cisco router, and set them up as your trusted internal network time protocol servers. Then have those 3 systems, let's say these 2 Linux boxes and the router, consult external time sources. So in fact, your router and the 2 Linux systems will become stratum 2 clocks. You then have all of your other systems such as Windows, Red Hat, Debian, so on and so forth, synchronize against those trusted internal time resources, and they'll be at stratum 3. But ideally have your internal hosts synchronize against your internal stratum 2 or 3 clocks, which reference outside sources. And of course, if you have an external time source such as GPS configured, then by all means use it and you'll become a stratum 1 server. So it's hierarchical, it works by default. NTPQ handles the display of information. We've been using NTPQ with the NP option to not display names, but, and notice at this point, the asterisk is assigned to the GPS clock, the stratum 1 clock, indicating this is our trusted clock. And there are candidates included with the plus symbol, candidate clocks, other clocks that are to be trusted, including the Red Hat Enterprise stratum 2 and our internal stratum 3 clock. Whereas it doesn't trust the 199 clock, which again could be some sort of IP tables which we haven't looked into. We'll look at it in the security section, reason why it's not communicating. But it has assigned a stratum 11 to it. You drop the N option and it will perform name resolution. So here's a name resolution. We're currently trusting bigben.ucsd.edu. This is our clock. But name resolution returns when you drop the N option, just like using netstat. This NTP-Q utility is both interactive and non-interactive. Run it with no options and it propels you into interactive mode, at which point you can type help to see the different commands that you may execute, such as associations. And this returns the different associations, reachability, so on. Peers. These are other clocks that you've paired up with. And many other items. You can print a current time, see the version of NTP that's currently being used by the NTP daemon. Again, it supports multiple, but it's claiming to be version 2 for compatibility reasons, and you can force that through the configuration, and so on. Again, NTP-Q is the main utility. Now, there are other utilities in addition to NTP-Q, such as NTP-Date, which can be used to immediately set your clock to the time of a remote clock. For security, there's NTP key generation, which allows you to generate a key, a synchronous or synchronized shared key, to be used between two NTP servers for security, to prevent other clocks from influencing your local system's clock. There's also NTP trace. This allows us to trace the path between our clock and our trusted clock. So it shows localhost, that's our clock, which is assigned stratum 11, and the stratum 1 clock that we ultimately trust. So it traces the path between the NTP path between our clock and the trusted clock. And again, other utilities like NTP time, NTP DC, but the key ones include NTP Q as well as NTP date and trace, and optionally NTP keygen for generating shared keys between servers. So the protocol is up and running. Just be sure that you start it, you set up the configuration, then start it, and ensure that check config enables the clock. And if you see that you're unable to synchronize with an internal clock, chances are IP tables or an ntp.conf directive is blocking it. You can just man NTP to find out more information about a directive that could be blocking. It's usually a restrict directive. So with that said, we've looked at NTP, and we're going to move on to other daemons.